Thank you very much. My name is David Ward. I work for Cisco Systems, but this morning I'd like to represent basically the community of folks who work on routing protocols and signaling protocols, because there's been an emerging trend over the last 4 years on a promise made about 15 years ago that routing and signaling protocols could be made highly available. Over the last 4 years, in a number of groups at the IETF, again, this common thread has emerged, but it's been difficult to find its way through because there hasn't been a unified discussion on the topic. So what I'd like to do is talk to you about non-stop forwarding highly available routing and signaling protocols by describing the problem, presenting the solution that's emerging, because it is a common solution throughout being applied to all the protocols. Talk specifically about BGP, the IGPs, Multicast, MPLS, a bit of infrastructure, because it's not just all about the protocols themselves. But overall, what I want to talk about is not how the bits and bytes are lining up in the protocol headers or whatever the case might be, but in fact what is going to happen to your network, what your customers are going to see, and what this impact is going to have on your network in general. Overall, the problem can be stated that we need to increase network and node availability during planned and unplanned software restart or hardware changes. The period that we've been in right now is that upgrade and downgrade of software is very high impact. All traffic goes around a particular node, and the router stops functioning. Packets stop flowing. Instead of non-stop forwarding, there's full stop forwarding in the router itself and in the network. The topology change can be seen across the network, regardless of how long the duration might actually entail. Routes are going to flap through the network and external to your network potentially. There will be traffic oscillations, as you know. As a node goes down, your traffic has to reroute around that. You have to engineer for the traffic oscillation and the increased load across links that were not originally necessarily engineered to handle that particular load or spike during the planned or unplanned outage. Also, as we all know, networks are becoming increasingly complex, and the length and duration of maintenance windows is getting shorter and shorter, and the amount of work that needs to get done as networks become more complex gets longer and longer. And so some of these extensions might actually begin to alleviate that particular problem. So overall, the potential solution can really be summed up effectively in my first bullet here, which is that you are attempting now to recover state from your network peers and adjacencies. You can do a bit of optimization by comparing with a local checkpoint or a local state cache of what the peer state was before you did the restart and set some timing variables. But also what's key is that, as it's been specified, you do not have to try and keep TCP or transport state during the outage duration. Instead, you put the peers into a new state, thus making it easier to develop and deploy in your network. But it is something you need to take notice of, because in the past, a number of potential customers of yours would take a look at the BGP neighbor state, and if it went into down state, they would plan that as an outage because, of course, in the past, packets stopped flowing. Now there's this new intermediate state, which I'll describe to you, in which packets keep flowing, but the state does transition. So the second point is that, of course, it has to be negotiated across your network, because we can't just have, introduce this new feature through a flag day. Also, you have to be able to, of course, migrate router to router and peer-to-peer relationships to handle the new feature. So with non-stop forwarding, basically, the point is that service level agreements for packet flows can be preserved. There's no sudden oscillation of the traffic in the network, as I mentioned, but again, peering state and adjacency state does change. No flapping routes necessarily across the peering points, whether it's external BGP or internal BGP. And then the fifth point on this slide is that naturally, and of course, Multicast, Unicast, and MPLS all have to have specific approaches to this particular problem, because they have very different network characteristics, and so different solutions emerge for the different technologies and the different solutions. So moving forward, the potential solution, you're going to see also that the key is how long it takes to detect the outage, restart the process or board, and reconverge within a specified amount of downtime that is configurable. Not only can it work within as you'll see, the specified timers of downtime for each protocol, whether dynamic routing or signaling, but also it has to be overridden by what you want to have your network do. And so you'll see that this is configurable as well. Clearly, we had to handle the cases of when nonstop forwarding and the extensions to these protocols have to be aborted. In all cases, whether it's potential multiple planned or unplanned failures or whatever the case could be, you have to have the control to be able to abort this feature, as it might not do the right thing in your network. Also, what has been attempted to occur by the protocol developers is that there are both, in many cases, protocol extensions that are not required to achieve nonstop forwarding high availability, and I'll walk through an example of those as well. Of course, or in general, those that do require protocol extensions over time are generally made because convergence properties are in fact better by making those extensions, and I'll describe those a bit as well, and hopefully it'll be clear. Another key thing is that we don't want to have to carry more information in the update packets between peers or between adjacencies. We're already worried about convergence time, we're already worried about increasing size of packets and increasing load, and we don't want a feature like this to necessarily require more compute time or more load upon the peers that of which you may have disparate router capabilities, thus overloading one particular router or another. Also, the last one related to the previous topic is that we don't want the new updates, link state announcements, or link state packets to have to change their stuffing properties. In other words, we don't want to necessarily now have one prefix per update packet or something which would again increase load in your network unnecessarily to drive this feature. At the same time, we do want the ability to be able to control this on a per address family, sub-address family, and MPLS characteristics in each update packet, so that way you can once again control even further what you want to have nonstop forwarding enabled and what you want to be highly available. So let me describe what you'll see in BGP when you turn on this particular feature and what it looks like. And I'll walk through what you see on a receiving peer who receives a I'll be back message or a graceful restart message, and what you'll see on the restarting peer. And then we'll go a bit further into the other protocols and infrastructure. So the goals that we want to have for BGP and its behavior is that the routing table is recoverable from peers without keeping TCP state whatsoever. Host state and transport state should be and is able to be separated out from protocol state itself. And in fact, the TCP socket will be closed during a graceful restart. The extensions need to work for board failover, software restart, or peer reset of any particular flavor. And of course, as I mentioned, you have to be able to limit the number of graceful restarts if a peer gets into a temporary state where it's constantly restarting. That, again, your network would be out of sync for too long of a period of time, and in that particular case, you want to shut down that peer. We don't want to get into a tight loop of constantly restarting while it's graceful or ungraceful, of course. The graceful restart in BGP, as I mentioned, is negotiated either at open time or through recent extensions in BGP. It can be dynamically negotiated during an already up peering session. So that way, depending on how you want to transition to deploy this particular feature, it doesn't require a flag day or a restart such that you can continue with graceful restart beyond that. Again, it's a deployment consideration. So the actual extensions that are required to turn this on BGP are actually fairly simple. Basically, we have to add an end of rib marker, because as we know in BGP, there's no sequence IDs in update packets yet, such that you can't necessarily tell when you've received a complete rib or a peer's notion of its complete rib. So that way, we've added the end of rib marker. Of course, you have to have the graceful restart capability, as I mentioned, in which you'll have a graceful restart capability that you negotiate per address family v4, v6, and per sub-address family unicast, multicast, and it also has an extension for MPLS as well. And the capability can be negotiated, and you can control your network to determine what you want to have happen along these boundaries as well. So flexibility is there. On the receiving speaker, when you receive a graceful restart message from a peer, the first thing you're immediately going to do is take all the prefixes you've learned from that peer and mark them as stale and put them on a purge timer immediately. So this purge timer is ticking in the background no matter what. When the peer comes back up and you receive the new open message, you stop that purge timer. Now, the point of this purge timer is that if the peer doesn't come back within the specified interval, and currently specified interval is 180 seconds, which is quite a long time, you might not want your network to be out of sync for that period, for that duration. You might want to control how long that peer can be down for, and when you receive that open message, so that way if something did go catastrophic, whatever the case, you could detect that earlier, and potentially even earlier than the current default 180 seconds. So again, the peers come back up, we stop the purge timer because the peer is back. And what we do is we now start another timer which waits for the end of rib marker from that particular peer. Now the point of waiting for the end of rib marker really is so that you have a finite amount of time which you've configured in which you want to get back into sync and reconverge from that particular peer. So the end of rib timer is going to fire when either an end of rib message is received from the restarting speaker, and what happens is if you have not received the entire rib within, again, that particular timer, what you're going to do then is just assume that those routes are stale, they haven't been refreshed from that peer, and you're going to get rid of them and purge them from your forwarding table. So you've controlled how long the peer has to come back up, and you're now controlling how long you're going to give that peer to actually send you all of its rib data. So again, point number 4 is if the purge timer does fire, you're going to remove all the stale routes. And of course, if the peer comes back up but doesn't have graceful restart capability announced, you immediately just purge all the routes from the particular peer. This could be in that upgrade-downgrade situation in which you downgrade because you suddenly want to use a different feature on a different particular rev of software, or whatever the case could be. Now on the restarting speaker, a couple of things have to happen. So now you're the peer in which you want to graceful restart. What you need to do is you need to configure how long you want to hold on to the RIB or database of routes that you've received from all your peers, because if you can't come back in time and renegotiate between them, you need to purge your data and tell everybody that it's stale as soon as possible. So on this particular box, you're going to configure how long you're going to hold on to your data. So what you do at that point is you send your opens to your peers, and you wait for end of RIB markers from all of your peers that are graceful restart capable. Again, this can be run in a mixed network for ease of deployment as well as where you want this to happen in your particular network topology. So as the restarting speaker, once again, you've configured your timer, how long you're going to hold your data, you send out your open messages, you get your open messages back from your peers, you then start reconverging by receiving the data from your peers, and you wait for the end of RIB markers from your peers. Once you've received all of your end of RIB markers from your peers, or the update timer fires, what you do is you calculate your best paths. So what we're doing here is we're optimizing to only send out the new prefixes that we would have selected during any kind of topologic changes that would have happened during the graceful restart period. So what we do is we update our RIB, again doing a mark and sweep potentially. We generate all the updates and we send them out to our peers. We send them our end of RIB marker, and we hopefully have optimally reconverged for either the duration you want between peer outages or the duration that you want your network to be out of sync through the end of RIB timer. So again, once you've sent all your packets, you sent out your end of RIB message to all your peers. And what you've also tried to do is attempt to cut down the number of extra packets, extra update packets or routing protocol packets that you need to send between your peers and try and optimally reconverge. So moving on to the IGPs, because as we know, this is really interesting for external BGP, but internal BGP relies upon either ospf or ISIS to calculate the next hops and where traffic is going to be sent across your network. So for ospf, I'm going to talk about a specification which requires protocol changes, and for ISIS, I'm going to talk about changes that are not specified, but that can enable nonstop forwarding. And then I'm going to talk about version 2 of nonstop forwarding for ISIS, in which protocol extensions are required. And also, in ospf, there's a second extension to the or there's not an extension to the protocol, but nonstop forwarding is enabled as well. But I'll just give the example in ISIS. So the goals of the IGPs are rather and remarkably similar to what we wanted to do for BGP. The IGPs have to be able to recover and rebuild state information from the neighbors before the adjacency timers expire. Now, of course, these adjacency timers are controlled by you as well in your configuration. You can leave them as default, or you can change them to what you want them to be, but of course, that will necessarily create the situation where the protocols will go through a mark and sweep and potentially can't reconverge optimally. So, for the fastest recovery of either OSPF or ISIS, all neighbors must be NSF aware for the fastest recovery. There are other protocol enhancements for the nonstop forwarding unaware neighbors that are a bit slower, and we'll talk about that in ISIS. And like BGP, the IGPs must reinstall their prefixes within a specified purge timer that you configure as well. So like in BGP, you can determine or you can configure how long you want your network to be out of sync. It can either be the default, or it can be shorter than that, or it can be longer than that, depending on the properties of your network. So that's configurable, as well as for the IGPs, we have to be able to handle carrying traffic engineering data, and in fact, these extensions are equally suited for either V4, V6, addresses carrying multicast traffic, as well as carrying traffic engineering information. So here's a really high-level flow of what OSPF looks like during a restart. So effectively, you've got to configure on any box whether or not you want nonstop forwarding or graceful restart for the IGP there. So the process restarts and reads that configuration. For OSPF, on all of the interfaces in the upstate that the IGP detects when it comes back up, it'll send out a hello with a specific resync bit set, really straightforward, rather similar to BGP. We're going to wait for n seconds, where n is determined by you and configured by you to learn about all of the neighbors. We start our link state database resynchronization with all of our neighbors. We run a mark and sweep through our LSDB of what we've received and the topologies that we've received from our neighbors, and we generate a router LSA. We run our SPF algorithm, and then we flush anything that's stale in our link state database. Again, you can see that it's a really similar solution to what's happening in BGP. As I mentioned, nonstop forwarding in this feature has to be able to be controlled when it needs to be aborted because of some kind of failure situation or catastrophic event. So on the restarting router, nonstop forwarding is going to be aborted when any of the neighbors are nonstop forwarding incapable, because then you can't resync your database without setting the special bits or having your adjacencies understand these particular bits. Also, nonstop forwarding is going to be aborted if the resynchronization doesn't get completed within the configured dead interval. Again, you're controlling how long you want your network to be out of sync. And nonstop forwarding is going to be aborted when there's one or more neighbors also attempting to gracefully restart at the same time. In the particular situation where you have more than one, although the mathematical proof shows that potentially you can get back to a synchronized database, right now there's many different interesting state transitions you can get into, and it's just plain easier to deploy, in our opinion, when you don't have multiple neighbors attempting to restart with nonstop forwarding and everybody resync through their database. On the adjacent router, nonstop forwarding is going to be aborted again when there's one or more neighbors attempting NSF, or when there's a change in topology when nonstop forwarding is in progress, and that's configurable. So if you're worried that a topologic change occurs while you're attempting to resync your database and potentially you're afraid that the protocol can't handle it, you can configure that if there's any topologic change detected, don't run nonstop forwarding, reinit the entire adjacency as it always has, and continue. Moving on to ISIS, nonstop forwarding version 1, effectively it's an extremely simple way that today ISIS can be restarted in a graceful manner without any protocol extensions whatsoever. But there's a couple of key things, as I mentioned. It's a pretty straightforward extension. Effectively, you have to be able to recover with your adjacencies before the hello timers expire. In other words, what you have to be able to do is send a hello or receive and acknowledge an LSA within ISIS within that before the hello timers expire. And again, it's a 3 strikes rule, and you can configure how many in some cases and what the duration or interval is in between the hellos that are being sent. This particular one, as I mentioned, interoperates with unaware adjacencies, but it is simplistic, so you use this kind of configuration knob for how long it's going to take, how long you want your network to take for convergence to occur. So you also have an interval between the maximum or the minimum amount of time that you're going to allow between nonstop forwarding or graceful restarts, I apologize, and then a timer for how long you want to allow a route to be maintained in the database in between restarts or during a restart duration. So in other words, you set the time, converge my network within n seconds. If the network doesn't converge within then, automatically purge. But in fact, what's nice about it is that you don't have to change the protocol at all. So just let's walk through the state machine. It's really quite straightforward. So what you do is you've checkpointed your adjacency database so you know who you had adjacencies with before you restart. You quick read that. You enable your sending of packets, start sending hellos to those restored adjacencies. You read the checkpoint table of your link state database. You begin to restore your LSPs. You enable the I/O, input-output of the LSPs. You start requesting the checkpointed LSPs that you have on specific circuits. You restore those LSPs. You start checking LAN circuits next. You restore the LAN circuits. You start synchronizing point-to-point circuits by doing the typical handshakes that you've configured on those particular links. You then restore those LSPs. Here's the configurable knob in which you listen for new LSPs, and you just set a really simple interval in which you're going to allow new LSPs to arrive. You run your layer 1 SPF, you run your layer 2 SPF, you resync your new state back within the RP, and then nonstop forwarding restarts complete. So it's all done with the magical, how long am I going to wait to listen for new LSPs, and a couple of local checkpointing hooks on the RP itself. So ISIS nonstop forwarding version 2 is, again, a simple extension following the initial work done in BGP, where you're kind of sending the moral equivalent of an end of rib in ISIS. But here, it's basically two packets you need to send. One is the restart request, magically like the graceful restart graceful restart knob being sent in BGP, and the second one is the restart acknowledgement, or RA packet. So those are the two new options that the hello packet in ISIS has. And effectively, how it works really straightforwardly is when you receive a restart request, you start refreshing the adjacency and the link state and the topology learned across that adjacency boundary. And then when everything is resynced, you send your restart acknowledgement, and then you know you've received the entire topology that you're supposed to have received from an adjacency, and you can optimally remove anything that hasn't been refreshed in the topology. So moving on to multicast. Unicast has had a pretty common theme working through, which is announce you're going down, do a mark and sweep on your database, send a notifier when you've received everything, reconverge, and continue forward. Multicast is a bit different because of the properties of multicast networking. And really, you have to have an understanding of the two different pieces running inside the router and how multicasting works. You have to have a notion of the control plane and what the protocols are doing, but the forwarding plane also has to have enough intelligence to be able to plug back into the control plane as well as control the forwarding itself, because multicast could unfortunately be, the internet packet gun, which we don't want to have happen. And the other thing is the forwarding plane can actually detect routing loops and make intelligent decisions for you at that particular point. So again, there'll be a timer for the forwarding plane, so that way it only forwards multicast packets long enough for the control plane to restart, and to avoid the internet packet gun, put a rate limit on multicast traffic. So again, following the same pattern that I've mentioned already, multicast nonstop forwarding follows the same thing by checkpointing some critical state necessary to optimize how to restart and how to restart more quickly, add some done messages like end of rib to the multicast routing protocols, and of course the forwarding plane has to be NSF aware to be able to plug back into the control plane. What is checkpointed? What is that important data? Well, the grouped RP mapping and the RPF rib in multicast. That'll just allow you to reconverge more quickly. What isn't checkpointed, and what state don't you have to keep? Well, again, PIM has been extended to be able to recover from its network peers. IGMP has been extended, can recover from the network. MSDP cache is also recoverable from the network. As I mentioned, the forwarding plane has got to be able to detect loops and shut down those routing loops so that way we aren't spraying data unnecessarily down links that don't have any receivers there, as well as we don't want to get into a tight loop in the network and just destroy links unnecessarily. So basically, during the update process, any multicast forwarding entries that have been updated can send out a PIM assert to designate the forwarder, even if the unicast is not converged. And I'll walk through a bit of state of when the control plane fails and how this works in a moment. Also, the forwarding entries marked old, again during the mark and suite, remove the interfaces from the O list if they receive any data matching on it. So that way you've clearly detected a loop, take it out of the O list, you won't send packets down that particular link anymore. So pulling it together, if you followed what I've mentioned for BGP and what I've mentioned for the IGPs, and you pull it together with the example of the multicast control plane, you see once again the pattern that's emerging, and here's a little bit more data of what it actually looks like when the RP, for example, you want to do a swap out of the RP. So in this particular case, when you want to upgrade a piece of hardware or swap out a piece of hardware like the RP, both unicast and multicast protocols are going to go down. That's pretty straightforward. The forwarding plane, again, has to have enough intelligence to detect the fault, starts to initiate the nonstop forwarding action. What does it do? Again, the old mark and sweep. It marks the multicast fib entries as old. It begins to rate limit the total amount of multicast, as I mentioned, and then we start a timer for the refresh on that multicast fib before it runs a sweep. All the control processes are now restarting. The multicast rib is holding back multicast fib updates so that way we can reconverge and not thrash our forwarding tables and again start spraying packets all over the place, as well as we want to refresh back to the state that we were in. And any intermediate state, as we're learning information from our peers or adjacencies, will cause us to thrash our multicast fib unnecessarily, and we won't be comparing the state we were in to the state that we're going to be in, which is fully converged, both multicast and unicast. So the multicast unicast rib begins to restore prefixes from the unicast routing protocols. IGMP gets its updates, propagates those to the multicast rib. IGMP sends it done, so that way the multicast rib understands when IGMP is done. PIM refreshes itself with its network neighbors, and from IGMP an update the multicast rib. Sends a done message to the multicast rib, as I mentioned. When the multicast rib gets its finished message from PIM, then it starts updating the multicast forwarding table, because now you're again comparing the state that you were in before you decided to switch over your RP board. The multicast fib starts receiving the updates. We start reinstalling at the route granularity. We now can refresh all of those prefixes in the multicast fib. We sweep out anything that hasn't been refreshed. When unicast reconverges, we receive the done message. That way we can resolve all the next hops for any of the multicast traffic. We remove the rate limiting, and nonstop forwarding is complete. And we've compared where we were with where we want to be. So we've made it through unicast. We've made it through multicast, how that's going to work. We've got a few things left. Let's talk a bit about MPLS, which I'll go through quickly. Then we'll talk a bit about the infrastructure, because it all has to hold together, as I mentioned, within the control plane, and then I'll sum it up. So in my only picture in this slide set, basically MPLS is going to follow the same principles that we did with the relationship between unicast and multicast, and then tie it together, except it's going to use potentially a slightly different way of modifying the forwarding table for for basically no packet forwarding issues whatsoever. So the traffic engineering database clearly is created by ospf, BGP, and ISIS. So that database itself can be recovered from those particular protocols. There's no reason not to, once again, just rely upon the producer of the data to refresh your state. The signaling protocols, both RSVP and LDP, have been extended to recover in the same manner as BGP and the IGPs, as well as multicast, to recover from its adjacencies and neighbors. The label manager, or the actual database to be installed, that sits also in the control plane to keep state across all the line cards, well, that can be recovered from the layers up above. And then the label fib actually sitting on your line cards that's forwarding for you through those tunnels. It's going to take a new step in which it actually now takes the new label fib that was created on the control plane, install it, and then do an update of a pointer, and then you'll have no packet drops whatsoever. Now, what's interesting is that MPLS already has node protection. It already has fast reroute to go around particular nodes. So I'm not necessarily advocating the use of this particular feature, but it can be useful to you if you want to do upgrade, downgrade, if you don't want to necessarily move your traffic onto your backup links, if the duration is going to be short enough, or because auto placement currently isn't enabled on MPLS and you don't have every label switch path going through this particular router backed up with a fast reroute link, maybe you just wanted to use these protocol extensions. So caveat emptor on whether or not this is particularly useful or necessary in your particular network. And I pretty much have walked through the next bullets on the slide again. The traffic engineering database is recovered from the protocols. RSVP and LTP have been extended in the same manner which I've already described. We do have a little bit of local checkpointing of data for an optimization, but the key now is that we can wholly generate, refresh, recalculate our label fib or LSP fib, download that to the line cards, update a pointer, no packet drop, either for the case of unicast, multicast, or now MPLS. Moving on to the infrastructure, because it's all got to hang together, because we've talked about the interaction of a number of processes, a number of applications, and if the infrastructure isn't also nonstop forwarding aware and capable and able to handle this situation, the router or your network will not be highly available and you will have packet drop. Again, the goal is to keep packets flowing through the node. Again, one way to do this is to use some of the principles that I've just described of how the protocols are working. And so there's a few things we've got to take care of. The route downloader between the RIB, the database of the prefixes you've learned from your peers and adjacencies, and how those prefixes get down to the fib through the downloader. The RIB has got to be able to handle protocol restart, and then we've got to be able to handle RIB failure or RIB restart if for some reason that's part of the upgrade downgrade situation. So for the downloader, when it restarts, basically the RIB can detect the failure. I'm not connected to this particular application anymore. It associates any state, download state that it was in between the RIB and the fibs, and then basically what happens is, down on the line cards, the fib clients are informed of the restart because they also have lost any connection with the downloader, and they once again mark their routes for deletion. This should all be sounding familiar as we're reusing the same principles again. Once the downloader retrieves all the routes from the RIB, the downloader then starts, of course, passing it down to the line cards. The downloader informs the fib clients when the entire RIB is there, because again, we know what's in the database, so we know when we start, we know when we end. And anything that isn't refreshed down in the line cards, the fib clients can purge the marked routes, potentially on a configuration knob, depending on the implementation. Protocol restart, as I've talked about for most of the time during this presentation, the RIB can detect the restart of the protocol as the applications reconnect across any particular application programming interface. And in the RIB, it's going to, just like we did between our peers, do a mark of anything we've learned from that particular protocol, set a purge timer for those protocol routes, where that duration could be a configuration knob. The protocol restarts. It reconverges along the lines I've mentioned. It inserts those prefixes into the RIB. The protocol could inform the RIB when it's received all its prefixes because we have enough information from all our network peers to keep the intelligence inside the box. Anything that hasn't been refreshed, we mark and we remove. Or if the configurable purge timer hits, you'll remove the prefixes at that particular time. So what happens when the database, the big database in the router of the RIB of all the prefixes you've learned from your neighbors restarts? This also can be handled. So the RIB restarts, we start running our convergence timer, and we withhold any update down to the fibs until we receive effectively a message from the protocols, because again, we have enough information to be able to keep the intelligence inside the box. So the protocols detect the restart of the RIB. The downloader will also detect the RIB failure. It reconnects. It informs the fib clients of the restart. Fib clients could potentially create a new table, or the fib clients could begin to mark prefixes for the deletion. What I mean by this is that what could happen for either multicast or unicast forwarding is that you actually create the fib first in an independent table and then just do an update, so that way you have absolutely no thrashing whatsoever to either the memory space or affect the forwarding at all on the particular line card. So when the protocols insert the routes in the RIB, it informs the RIB that everything's finished. The downloader retrieves all the prefixes from the RIB, downloads them to the fib clients. RIB informs the downloader of convergence time, again brought in from the peers. or the timer expires and then things are considered done at that point because you've determined them to be finished, everything begins to resume normal operation at this point. And the fib on the line cards just switch over to the new table, and no packets have been dropped at all. Or the fib entries are going to be removed because you've determined that your network did not converge fast enough within the time period, and you'll just allow normal insertion of prefixes as happens in all other operations. So let me sum up here with a couple more slides. I've got pretty much the only marketing slide, which, in other words, routing and signaling protocol nonstop forwarding enables non-disruptive, meaning packets continue to flow through your network as you've engineered it and as you administratively control them during planned and unplanned software restarts, or during the upgrade or replacement of hardware, during the upgrade or downgrade of software. You can use the same mechanisms now to enable migrating your software version, and hopefully this will eliminate any traffic oscillations depending on the interval or duration that you've set your timers. So configurable knobs are enabled for local tolerance of graceful restart timing. Non-stop forwarding is going to be the key, and there should be there's necessarily no route flap either seen internally or externally. Instead, it's a refreshed database, and the topology doesn't necessarily have to change whatsoever. Then again, eliminating the traffic oscillations. Also note, EIGRP has also been specified, rather similar to ISI's nonstop version 2, but for I just wanted to focus on the specified protocols today. So, to sum up, what happens in your network and what do your customers see? They're going to see a new state of the BGP peering session. It's going to be stale state. It's not up, it's not down, it's during the refresh interval in which prefixes are being exchanged and you're reconverging. They will see the TCP connection drop. They'll see it go to fin, wait, or close, depending on the type of restart that occurred. So this is something that it would take some education of customers so that way they understand that when they see the TCP session go down for the peering session, traffic is still flowing. They need to watch the state of the peering session. Due to these extensions, there are no extra withdraw or announce packets. We aren't sending any special packets. And again, there's no longer any sending of withdraw or announce packets due to the planned or unplanned outage. Hopefully we aren't thrashing the network if it's not necessary. But in all cases, if we need to abort the restart capability, we have to be able to let the network know as soon as possible. We have to be able to configure it, and the network has got to be able to do the right thing according to current specifications and the current way that these protocols are deployed in your network. Note that not every router is required at all locations in the network. This can be deployed router by router or in pockets to be able to be enabled. And the network can handle a transition router by router because it is negotiated or dynamically negotiated potentially once the peering sessions or adjacencies have been up. There are no new black holes or routing loops necessarily created by these particular capabilities, Instead, in fact, the normal routing loops and black holes that we have to deal with in the network today due to specified timers could actually be alleviated because the recovery now allows you to specify how long you want each state of the graceful restart period to occur, whether it's how long you want to wait for a hello to come back. So if you think about the 3-minute timer in BGP, you now have a specific timer of how long you want that particular peer to come back and give you an open message, or dump the packets immediately. And another key thing is that not all address families or sub-address families or MPLS must be enabled with nonstop forwarding. This is not a ubiquitous feature in which everything comes. No, if you want to protect V4 from V6, multicast from X, Y, or Z, or MPLS, you can configure what address families, sub-address families, or extensions you want to be nonstop forwarding enabled or not. So I have reached my last slide, if there are any questions. Hey, Sue.
Okay, let's go through a few questions.
Uh-oh, 2 pages.
No, the back of it.
Oh.
Scribbling on the Nanog sheet. Why did you guys not decide to do the ospf opaque restart functionality?
Actually, I just presented one particular way of doing ospf, and actually with the extension that I described, opaque, LSAs are reflooded again, and you can actually reconverge any information handled in opaque LSAs.
Okay. I thought you just had
Yeah,
to send it.
it's actually the other draft that doesn't, but I didn't want to get into it.
Okay. One other thing is stuck with the MIB on BGP.
MIB, I'm sorry?
I said,
Check,
I'm
check.
stuck.
I'm kidding.
Somebody has to sweep the floor. Would this being a good MIB addition, how are you guys monitoring when the machines go into this particular state?
It would be an excellent MIB extension. We should work with Jeff right over there to have it done properly. Was that the right answer?
That was my bid for Jeff. You can say thank you, Jeff. There are three sources of BGP crashes that some of this doesn't identify, that which is bad prefixes, sending down nodes, over the max limit of prefixes, and bad AS path. What happens when this occurs? Is this attacked in any of this particular work?
So you're saying the particular case that you have two cases in which a notification would be sent which would bring down a peering session because there's some error, whether it's AS path or it was prefix.
Or in some cases, as the list just said, that doesn't really, some routers don't choose to silently ignore.
Sure. In that particular case, a couple of things would happen. In the case of bad information, you've received bad information and you don't want to recover that state. And so something's wrong with that peer and something's catastrophically wrong with that peer. And this isn't a particular case where an RP went down. This is actually bad data they're sending you. So bad data, take them down because you can't trust anything from them. So that kind of covers the prefix and AS path case. With respect to the max prefix case, right now, what could happen is that the peering session, it hits the number of max prefixes and the peering session goes down. If this was one-time aberrant behavior, you potentially would refresh the number of prefixes up to that max prefix limit, and hopefully things have been corrected. If they haven't been corrected, you would go through this restart period, potentially n times, where n is configurable, and then if it continues in this state, the peer would be brought down and held down. Okay,
so you have the same automatic restart that keeps going into this?
Could be.
Okay. And bad AS path. Is this like bad data?
Bad data again.
Okay.
If you get bad data, take them down.
Okay. Some people have asked on the list that not trash things because it tends to fluctuate.
So one thing, Sue, on the things I've described, also there's a number of new error conditions or notifications that are also being extended. If you note, what I described is kind of just generally above any specific and not allowing, or I'm not describing any case where you can have a specific policy for any type of condition you get into. Instead, it deals with a restart in a general manner.
And yeah, I agree. Just some people had, when I did the query on the BGP state machine, this particular topic was raised and bad start. So I just wanted to make sure people knew where your stuff laid in that.
I bet over time things will head such that you can have a configurable policy, I would imagine, although, with deployment experience helps a lot.
Yeah, which is a hint for people to give Dave that good deployment experience, I'm sure. The ISIS V2 portion, could you identify V1 versus V2 in your ISIS restart as far as the ISIS restart drafts?
Mike Shand.
Yeah, I'm sorry. I thought you were going to ask Mike. Mike's not here? No.
No, I think Mike's still in the
He's
UK.
just the Shand draft for version 2.
Yeah.
Okay. And lastly, the reason you didn't mention the MSDP is because the MSDP spec hasn't changed at this point. Is that correct? Are your stuff still on the spec?
It's still under work.
Yeah, so it's in the design group. So you've worked on stuff that doesn't match the 11 or the 6 draft.
Everything is work in progress.
Okay.
Actually, everything I've described is completely work in progress for a number of vendors at this point.
Okay. Thank you.
Sure.
Rauska from AYR Networks.
Hey, Joe.
So are there equivalent...
Could you speak up a little
Are
bit?
there equivalent developments with link level protocols, HCLC, ignore my keep alives, during this period, or do you not expect link to go down end to end? I mean, how do you?
So right now, I'm not necessarily aware of any extensions in that area. I was one level up the stack. So there may be, but I'm not exactly positive. Anything else? Thank you very much.